today is the gentle introduction to multimeters, because we need to check the test points on your Williams power board. So on a multimeter you can measure all sorts of different things. You can measure current, which is amps. You can do a diode test, and you can do a continuity test. And sometimes the continuity test is combined with a resistance test. But what we're worried about is the voltages on this side. So that one is for AC voltage, alternating current, and that one's for DC voltage, direct current. The same on this multimeter. That one is for AC, that one's for DC. On this one you have a diode check and a capacitor check that you can get via just switching. Press that button and it switches between the two. You have a continuity check and a resistance check on the same setting by just selecting that with that. So this is a better multimeter. This is sort of upper lower class, and this is upper middle class. It's not quite a fluke yet, but it's very nice. So, but any El Cheapo multimeter will be good enough for what we're trying to do here. Okay, so to test between 2 points, you can just use the probes on their own. Put that onto the ground point and put that onto the test point you want to measure. But sometimes you need your hands free for other stuff, and sometimes it's just finicky. So I've got these things, they're called test leads, and I can then just grab onto the black lead and the red lead like that, and then I can clip those, either both or just one of them, normally just the black one, to the test points. The black one will stay on ground, this one will move around. So I can clip it on, take my measurement from my multimeter, write it down in a little table. So here's what I normally have. It's a little table with the test points, and then I measure the DC voltage and the AC voltage and write it down, next test point, and so on. Right, so this is a diode, and its job is to let current through only in one direction. If you're looking at voltage coming from a transformer, you'll find that the voltage oscillates, the same as the power coming out of your wall socket will oscillate. That is called alternating current. Direct current, however, is if you're looking at a battery. Now, the symbol for a battery in a circuit diagram is just a long line and a short line. And if you measure between that and that point over time, you'll find just a steady voltage. That's direct current. So this is DC, and this is AC. The thing is, your logic needs DC, and what's coming out of your wall is AC. So somewhere along the line you need to convert AC into DC, and that is done with diodes and bridge rectifiers. I'm not going to get into the detail on how it's done, because on like the 20th take of this video I just realized that I don't have the skill to explain that properly. But anyway, so what it comes down to is this. Your diode on a schematic diagram looks like that. In real life it's a little canister with a line on. That line corresponds to that. So this is the anode, and that's the cathode. So, and when you put your multimeter into diode test mode, I've gone and lost my diode. Here it is. There's the diode, little canister with a line on the one end. So that's the anode and that's the cathode. So on the anode we connect the positive lead, and the cathode is connected to the negative lead, and what you should see is like half a volt or something. So some diodes go down to 0.1 volt and some diodes go up to 0.7 volts, but it's around a half a volt normally. If the diode has broken, sometimes it opens circuits, and then there's as if there's no connection whatsoever, and then you'll see an overload on your multimeter. Sometimes it breaks, well, as if it's a short, so then you'll find 0 volts. So now it doesn't act like a diode anymore, it just acts like a dead short. And that's a dangerous thing to have in your circuit. It will break other stuff down the line. So we need to be able to test diodes. Now a rectifier is a thing like this. You'll see lots of them on your power board, and it's actually 4 diodes connected between these legs. And the one leg is marked plus, and it's normally different to the others. The pole opposite it is the negative one, and the other 2 poles are called your AC poles. So how it works is this way. It's 4 diodes connected like this. That's known as plus. This is known as minus. This is an AC port, and that's another AC port. So there's a pin, there's a pin. So if you connect AC across there, when this part is higher than that part, in other words, it's pushing current from there to there, it'll push it out that way. And then when it comes back from your circuit on the negative pin, it'll pull it out that side. If it's the opposite, if you're in the bottom half of the cycle, it'll push it that way, and it'll come back and pull it this way. Talking about the current now. So on your transformer side, you'll have AC, which is these 2 wires. But on your circuit side, the current will always go out there and in there. So you've got your AC converted into DC from this. Now to test this thing, you need to do 4 diode tests. So actually that was stupid, but let me just draw it again. There's your minus side, there's an AC side, and there's an AC side. So the plus side is where the 2 cathodes come together. The minus side is where the 2 anodes come together. So to test this diode, you need to do a diode test that way, that one that way, that one that way, and that one that way. And it's, I shit you not, I know you're not going to do this, but just for completeness sake, because, you know, I'm here now, I've got everything out. So I've got my positive pole. I connect, that's where the cathodes are, so I connect my black lead to the positive. It's other way around, it's counterintuitive. But there's my black lead to the positive side, so black to plus, red to AC. See there, it even says AC. Sometimes it's just a squiggly line. But there's half a volt. There's half a volt. Now to check the the other 2 diodes, I'm going to connect my I'm going to connect my positive pole to where the cathodes are, or where the anodes are, and check the same AC circuits. So there's 0 volts. So this diode is dead. It's acting like a short. That diode is fine. So this whole bridge rectifier is gone. It's not well. On this rectifier, you'll see that one corner has been chamfered, and it's also been marked. And even if you look at it, the positive leg is slightly different to the others. So positive leg, that's a black lead. Let's just go AC pin, AC pin, AC pin, AC pin. This one's fine. Okay, so now we know how to make that these things are used to make DC out of AC. But what you find is that on your, if you're looking at it on an oscilloscope, because you have this waveform, let's just draw it, that's been flipped up, that's quite a big ripple. So as soon as this voltage goes below, let's say 5 volts, your logic will stop working because logic needs 5 volts to run on. So what you need to do is to put some of this little storage mechanism that charges up when this thing charges up, but when it goes down, it doesn't discharge as fast, it charges up again. So that little storage unit is a capacitor. So you have, let's say there's your AC voltage. It goes into your rectifier. Now rectifiers are normally just drawn like that for simplicity. So there's your plus, there's your minus, there's AC and AC. So over here, what you're getting out from here is that ripple voltage. But now you add a little storage capacitor, and now you have voltage that looks like that. It's sort of DC, but it has that little ripple in it. Now, if you set your multimeter to DC, you'll measure the average voltage there, which is the steady state average voltage. But when you set it to AC, you'll measure the size of that ripple. And the health of this capacitor is related to the size of the ripple. The bigger the ripple, the more stuffed your capacitor is. If you want a low ripple, you need to use a bigger capacitor. These capacitors tend to dry out after a couple of years and then lose their storage capacity, and then that ripple gets bigger and bigger and bigger. And if you have this kind of thing going on, and that feeds into a regulator that gives you 5 volt out, but the ripple is so big that the input to the 5 volt gets below a certain point, let's say below a certain threshold, then you'll have a ripple on your 5 volt as well. And if that ripple causes the 5 volt output to drop below 4.8, that's when your CPU resets. So this ripple, the bigger it gets, the more risk you have of your CPU resetting. So, okay, to make a long story short, I need you to measure the DC component and the AC component on all your test points, and write it down and keep it for reference. You can always go back a year later and measure the same test points again and see if that ripple is getting any bigger. If it's getting bigger, then we need to start changing capacitors. If it's not, you're fine. Those capacitors usually last a couple of years, but we do have something called planned obsolescence, where guys specifically go and choose capacitors that dry up after 5 years, and then they give you a 4.5-year warranty because they know 5 years later everything is going to pack up because your caps are going to cock, and then you have to replace all the boards. But what they do is they just replace a couple of caps and charge you a fucking fortune. But anyway, so that's my big brother version of it. But planned obsolescence is a thing. Look it up. This board here is the WPC power driver board. It takes power coming from the transformer on these connectors here, and it creates all sorts of voltages that the rest of the system needs through the capacitors, the bridge rectifiers, regulators, and so on. It sends it out on connectors that are sitting here, well, to the rest of the board. Right, so now the test points on here, you'll find a little test point right there that's unmarked, that has a big fat track running right through it. That is your ground test point. So I'm just going to connect my black lead onto that, and I'm going to set my multimeter onto DC volts for now. And over here there's test point 2, and it's marked test point 2 5 volts. So let's see what it gives us. So I've got my test lead onto there. So it gives me 4.97 volts DC. So it's 0.03 volts down from 5. It's fine. But I want to check if there's a ripple on it. Maybe it's not smooth. Maybe there's a little bit of a ripple on there, which the DC measurement won't give you. But if you switch to AC, that'll only measure the changing part of it. And the changing part of it is negligible. There's absolutely no ripple on that 5 volt. So the 5 volt circuit in this machine is absolutely fine. Let's do the same thing with the 12. Switch to DC, go to 12, That's 11.6. That's close to 12. And the ripple on there is 0.03, so it's 30 millivolts, so it's tiny. There's another 12 volt test point right there. That just comes through a bridge rectifier and a cap, so there's quite a substantial ripple on there. The 12 volt that's sitting on here comes through, I think it's this IC here, which is a regulator, which clamps the voltage down to a specific voltage, and they are rated. This one makes 5 volt, that one makes 12 volt, and it's what it's there for. This is like a crapshoot. It depends on the voltage coming in and that sort of thing. So let's go to test point 1. You see the ripple on there is 160 millivolts, which is almost 5-6 times higher than the one coming through a regulator. And the DC voltage is 15 odd, supposedly 12, but it's fine. So what you can do is, what I want you to do is to test the AC component and the DC component for all these test points, especially the 5 volt and the 12 volt. You can also check, there's a test point here, test point 6, 50 volts. There's a test point 8 here, gives you 18 volts. There's a test point 7, which I can never find, which should give you 20 volts. Ah, there it is, right above the ground. That one you can do. So make me that table of test points and AC and DC voltages, and then we can figure out, are the rectifiers okay, are the capacitors okay, and if there's nothing, if you measure zip, then we know it's a power supply feed issue. Then it's a connector or a pin or a wiring or a transformer issue. Then you have to dig deeper. I'll see if I can find the video of the header pins that are, see, this is a header row. This plastic thing connected to the wire, that's the connector, but that's called the header. And sometimes these pins heat up so much that the solder becomes crumbly and soft. And from the vibration on the machine, in that soft solder, it cracks and desolders itself from the board. Now, the best way to check it is to remove the board from the machine and check it with a decent pair of glasses. Because if you're just checking it with a multimeter, let's say you're going on continuity, you switch the machine to continuity, and a continuity test is basically just, is there a short between those 2 points? If there is, the thing will beep. Shows you that it's connected. Now, sometimes when you do the continuity test, you'll be pushing on the pin, and if that pin is sitting loose in a socket like that, the minute you push on it, it contacts the side of the pin, and it looks fine when you test it, but not when it's in normal operation. So the best way to check for those things is to remove the board. Continuity tests, I usually just I switch off the machine and I just check across these fuses. They say you need to lift the one end of the fuse to check it properly. Yes, I know, but if there's a dead fuse, you can find it very quickly with just a continuity test over the fuses. Okay, just to recap, the test points are test point 1, test point 2, test point 3, test point 4. Test point 5, which I think is that one there that's unmarked, which has the big track running through it, that's ground. Test point 7, test point 8, and we missed test point 6, which is in there. It says 50 volts. Okay, test points.